Fred Adams is here from the University of Michigan. As I think Fred is going to explain, there was this amazing article that Freeman Dyson wrote, I think in the 70s. 79 in Reviews of Modern Physics, where he asked the question, what would happen if the universe exists forever, basically. I think he called it life in the universe, something like that. And it was mind-boggling. I mean, I remember just being shocked, page after page, with the new ideas that I encountered in that amazing paper. And the only problem is that we've discovered a few things since 1979. And Fred Adams and his former student, Greg Laughlin, who's now the chairman of the astronomy department here at Santa Cruz, wrote a sort of revised version and reconsidered all these issues about from the beginning of the universe to the end, or the indefinite future. And so Fred is actually a dynamicist, and he's one of the world experts in how things move around, globular clusters and all kinds of things like that. But he has one of the broadest views of astronomy of anybody that I know. I mean, he knows about everything. You have to if you do this kind of review of the literature. So this is the kind of thing that we're expecting Fred to present. Now, Fred also is having trouble with his voice. He spent a week in Beijing breathing that terrible air and then being exposed to all the germs on the airplane. So he's going to use a microphone. So welcome, Fred. Yeah. Fred's lecturing today and then again on Monday, and then the first afternoon slot is the third lecture by Lenny Susskind, and then there's a long period for discussion.
Okay, well, thank you, Joel. Well, thank you all for coming. Can you hear the volume already? Okay, good. So, as Joel said, we're going to talk about the future of the universe today. So, what I'd like to do today, in short, is to give you the entire history of the universe from the moment of the Big Bang all the way to the end. There's nothing more cheery than after a night of partying to hear a lecture on the end of the world, right? So, here we are. And as Julie said, that my voice is a little scratchy today, so I can't be quite as loud and obnoxious as I usually am, but I will do my best. So, here we go. All right, so Copernicus taught us some centuries ago that the Earth doesn't lie at the center of the universe, right? Or even the center of the solar system. So we changed our viewpoint so that we went from an Earth-centered solar system to a sun-centered solar system. And since then, astronomers and astrophysicists and cosmologists have continually degraded our status, right? So we now know that we don't live in the middle of the galaxy, using those dopey t-shirts that say you are here out of the outer suburbs, right? And we also know from cosmology that the universe is homogeneous and isotropic, so that our galaxy does not live in a particularly important place. We've completely degraded our status spatially. So I want to float the following idea, that maybe we should also degrade our status temporally. In other words, the current cosmological epoch, which we tend to think is the most important because that's what we know, but maybe it doesn't really have so much significance. And more specifically, what I mean by that is that interesting physical properties, ones that generate energy and increase the entropy of the universe, will continue to happen just about as far into the future as you dare to imagine. And we'll see how far we can get on this program today in the next few hours. Now, there's another principle as we study the future of the universe, and that is that this isn't just idle exercise that we're doing just for the fun of it, although it is a lot of fun to study the end of the universe. But in addition, by studying processes that take longer than the current of the universe, by studying processes that haven't yet happened or have not yet proceeded to completion, we actually learn quite a bit about astrophysical systems in our universe today. And I will highlight today some of the examples of that. And then we're going to hit this harder on Monday. Now, before I launch into this discussion, let me define a unit of time for you. Right now, the universe is 13.7 billion years old, as I think you would learn.
13.8.
13.8 now, okay. Is 13.8 plus or minus 0.1?
It's now about 0.01.
0.05.
0.05.
Yeah, 0.05. So, It's kind of amazing that we can have this conversation, that we can argue about the third significant digit of that number.
Right.
That's just completely amazing that we can even have that conversation on the street.
It's based on the new quantity though.
Yeah, no, that's great. So that's one number you should keep in mind. The universe is 13.8 billion years old. For today, or at least for this discussion, we can round a bit. So in rough terms, that's 10 to the 10 years. And if you write the time in years, the exponent is called the cosmological decade. So right now, the universe is in its 10th cosmological decade. When the universe is 10 times older, it'll be 10 to the 11 years old, will be in the 11th cosmological decade, and so on. When you're going into far reaches of future time, it's more convenient to use this time limit than redshift or something else. So I will freely go back and forth between these units, and you guys just have to keep up. So, as you've learned already this week, one of the big achievements of the last, I would say several decades, but it keeps getting better, is that we have this beautiful picture from the Big Bang moment up to the present day. And you've learned about it already with very good lecturers, so I'm going to assume that you know all about this. And that allows us to write down the future, the entire history of the universe, past and future, as shown here. So we can divide the universe into 5 ages, as Joel mentioned. Before the universe is about 1 million years old, there are no astrophysical bodies, there are no stellar bodies. There's only particles. So the first 1 million years of the universe we've called the Primordial Era. That's the province of Big Bang Theory and many of the things that you've already studied. But sometime after 1 million years, you don't know exactly when, we're still studying that, the universe was able to produce its first set of stars. So the universe lit up. It left the dark ages and lit up. And we entered into the current era, which is called the stelliferous era. Now stelliferous simply means full of stars. If you look outside, what do you see? You see stars. Even those of you who study galaxies, usually what you look at when you look at the galaxies are the stars, the galaxies, right? Joel even has a t-shirt with the stars on them, right? So you don't have to look far to see the stars. And the point is, this isn't a coincidence, right? The point is that all of the but most of the energy that's generated in the universe today is generated by nuclear processes in stars. So stars are driving the universe at the present epoch. They will continue to drive the universe until about Cosmological Decade 14 or so, when the universe is 10 to 100 trillion years old. After that time, the stars burn out, and the universe changes its character quite abruptly, and we enter into the next era, which we've called the degenerate era. Now, the degenerate era isn't actually a statement about the morality of the future universe. Instead, it refers to the fact that degenerate objects will inherit the universe. As we'll talk more about in about an hour, when stars die, they leave behind degenerate objects. These are white dwarfs and neutron stars and, to some extent, black holes. After the stars burn out, these degenerate stellar remnants are the most important astrophysical bodies left in the universe, and they will carry out most of the interesting energy generation processes that will run the universe of the future. This will continue from, let's say, Cosmological Decade 14 up until, well, here we've already got our first uncertainty, and I'll say Cosmological Decade 40. The compact objects will run the universe until the constituent protons decay. But we don't know exactly when that will be, so I put in Cosmological Decade 40 as a placeholder. And I'll talk more about this again in about an hour. But after the protons decay, the only stellar-like bodies left in the universe are black holes. Now this is actually kind of interesting. You usually define a black hole with some rough definition saying that a black hole is something whose gravity is so intense that not even light can escape its surface. At this time in the far future of the universe, black holes will be the brightest things in the sky. And they will be generating most of the energy that's generated in the universe. Of course, the reason why they can generate energy is that light can escape their surface. It escapes their surface through a process called Hawking radiation. You may or may not have heard of this guy, Hawking.
Fair amount of discussion of that.
No, I figured. So that's where it comes into play, is once the universe becomes older than about 65 cosmological decades, Hawking radiation runs the universe. And it will run the universe until the largest black hole makes this explosive exit from the universe. and we enter into the fifth and final era, when there are no stellar bodies left. So that's the story of the universe. Instead of dust to dust, instead of dust to dust, it's particles to particles. We start with particles in the early universe. We build stellar objects, they go through degenerate objects and stellar black holes. But all of the stellar bodies go away, and we're left with particles again. So this is, in fact, the executive summary of the talk. So those of you who are really tired can probably snooze now. But what I'm going to do now is I'm going to go through the story in greater detail and fill in some of the specifics. So the story begins 13.8 plus or minus a little bit years ago. And here, as you've already discussed, we don't quite know what we're talking about in the following sense that before there was a universe, there was something. And that's the problems, or that's the subject matter that quantum gravity is trying to address. And I don't do quantum gravity, and I'm not going to pretend to. So instead of doing that, I'm drawing you this picture. So there was some high-energy space-time manifold, and 13.8 billion years ago, it launched itself into a trajectory so that it was expanding really fast. And that little patch of space-time has subsequently expanded to become our universe today. And we're not able to say all that much about this Big Bang moment. We do know that because of quantum gravity, we can't even define time better than 10 to the minus 43 seconds or so. We can't define space better than about 10 to the minus 33 centimeters or so. But what's I think truly amazing is that just after this Big Bang moment, there are actually things we can say. So if I jump forward to the record age of 10 to the minus 35 years, then we enter into the realm of inflation, when the universe is expanding rapidly. Now I know that you've had lectures on inflation, so I'm not going to give you a full lecture on inflation, but I want to make one point that may or may not help you understand this phenomenon. Because this acceleration of the universe, which happened during this little time window here, in the early universe, is also starting to happen again, for a slightly different reason. So what does it actually mean for the universe to accelerate? It's actually a good question. Most people, or many people, say something about how the universe is expanding faster than the speed of light, which isn't actually a very good description, because the expansion is given by an expansion rate, which has units of 1 over time. And the speed of light is actually a speed, which has units of length over time. So saying that a rate is faster than a speed is actually kind of like saying a pound is bigger than a foot. It's not clear what the hell that means. So I would argue that the way to understand acceleration of the universe is the following. When the universe gets older, two things happen. Okay? One is that space is expanding, because the universe is expanding. And the expansion of space in between objects, like galaxies, the expansion of space tends to disconnect the universe. Because you're creating, loosely speaking, you're creating new space between points in space. So you're disconnecting things. Now at the same time, the universe is getting older each second. And that means light signals have more time to propagate from point A to point B. And the connection by light signals tends to connect up the universe. So when the universe is expanding, two things are always happening at the same time. You're always disconnecting the universe by expansion. And you're always connecting it up by light propagation. So basically you have two choices. Either you expand so fast that you connect, or you disconnect faster than you connect. Or you expand slowly enough that you connect faster than you disconnect. Those are your only choices. An accelerated universe is the fast case, where you're disconnected. Now, as you've already heard, if you have this little epoch, it lasts, let's say, 10 to the minus 35 seconds in the early universe of this disconnecting expansion, then you can understand a lot of the properties of our own universe with one little theory. You can understand why it's big, why it's old, why it's flat, why it doesn't have monopoles, why it moves to its current age, why it produces density fluctuations that we see in the micro background. And I'm sure you've all covered this. But this same disconnecting idea will soon in our near future come back and affect the future of the universe. And I'll show you a picture of that later. So now, we're going to jump forward in time to when the universe was, let's say, a microsecond old. Now, sometime between the epoch of inflation and when the universe was a microsecond old, the universe was somehow able to generate an asymmetry of matter or antimatter. So, at this point, cosmology is an experimental science. So I want you to do an experiment. I want you to touch the shoulder of the person next to you. Okay, now, the point of this exercise is that nobody exploded, right? Now, what that means, to a good approximation, is that the person next to you is probably not antimatter. Right? Now, astrophysicists have done this experiment in a little more detail and a little less directly all over the universe today. And what we find, or what we think we find, is that the universe is all made of matter, and we have not found any antimatter. We see secondary antimatter particles produced, we understand that, but we don't see anti-galaxies. So we think that in the first microsecond of history, the universe produced this asymmetry between matter and antimatter. Now the asymmetry back then was actually quite small, even though it's big in this room, it's all matter, no antimatter. Back then, there was a lot more particles around because there was radiation following them, and the matter was in the form of quarks. So for every 30 million antiquarks, there were 30 million and one quarks of ordinary matter. So the size of the asymmetry measured by quarks at this time is 1 part per million, which is a small asymmetry. Now, subsequently, the 30 million antiquarks, not only 30 million of the quarks, the remaining 1 part per 30 quarks confine themselves into things called hadrons, which basically to you means protons and neutrons. And then that is what's left to make stars and galaxies and planets and people. Now, why am I going on about this? Well, here's the thing. Some process was able to generate this asymmetry. There is some process out there in physics that we don't fully understand, we're still working on, that violates baryon number. Either that or you had a very wacko initial condition. But putting that aside, there has to be a process that violates baryon number. Now, what that means is that the universe is in some sense doomed. Because if there's a process that violates baryon number, then protons must eventually decay. And the reason is simple. There's a lower energy state available to the proton. The proton can turn into a positron. The positron has 2,000 times, a factor 2,000 times less mass and charge. It's a lower energy state. So if there's a path to get there, eventually it will. Well, we know there's a path to get there because there's an asymmetry.
Could you get matter antimatter asymmetry from slightly non-uniform expansion during inflation?
You need another ingredient. You need baryon number non-conservation. You need out of equilibrium configurations and
CP violation.
CP violation, right?
So the Sakharov 3 conditions.
Yeah, it's the Sakharov 3 conditions. So people have tried to build those 3 conditions into an inflationary scenario where you're out of equilibrium and whatnot. They've tried to do that actually in the reheating portion, which is when you're turning the vacuum energy back into real energy. Well, not real, but that's not real, but other energy at the end of the inflationary era. They've tried to institute those 3 conditions there. I don't know if that's exactly where you're going, but that's where people have built models.
Well, I was thinking about stuff independent of that, like just in terms of, let's say there was an asymmetric expansion.
Well, the asymmetry of the expansion itself won't do it. You need these other 3 things. And it's not clear that the asymmetry of the expansion will actually help you in that regard. Unless it were so severe that you, yeah, we know we can't have too much asymmetry because the micro background is so nice, right? You've seen pictures and I'll show you a picture. The micro background is really nice, right?
I'm thinking of something that which might have been smoothed out toward the end of inflation, but like imagine that there's a full antimatter universe over there that's very, very far away.
Well, I guess you're allowed to have an antimatter domain of the universe that's very, very far away. But the experiments say that it has to be outside our horizon today. So it's almost not really on the table anymore once you put it outside the horizon. Because you can postulate anything you want outside the horizon, almost outside the horizon, and not affect physics inside the horizon where we can actually do physics. So you got a question now?
This might be silly, but does dark matter has its own antimatter, like anti-dark matter?
No, that's actually a very good question. It depends on what the dark matter is. But the usual picture is that a dark matter particle is its own antiparticle, so they can annihilate each other. But they don't do that very often because they interact so weakly, and because the universe is so diffuse, I guess. So you can easily have cross-sections of interaction like we think we have, and put dark matter particles in the halo like we think we have, and not have them annihilate until about 10 to the 25 years, which I'll put on the calendar later for you. Okay, so we're only 1 microsecond into history, and we're a half hour into the lecture, so I have to speed up a little bit. So what happens next? When the universe reaches the age of about 1 second, then the dark matter particles are annihilating with each other, and they fall out of equilibrium, and you're left with some residual amount. And that process freezes the abundance of dark matter particles to the abundance we see today. And Joel's talked about this at some length. Joel's 4 hours of lecture are all embedded in this one slide. Now, after 1 second, then the universe is finally cool enough that nucleons can interact with each other. So we have protons and neutrons before 1 second. During the next 3 minutes, protons and neutrons get together and make light elements, deuterium, helium-3, and especially helium-4. And one of the triumphs of Big Bang theory is that you can simultaneously explain the observed abundances of helium, deuterium, and lithium.
Except maybe not lithium.
Oh, there's a
I
lithium
already
problem.
warned them about lithium.
You warned them about the lithium problem. I was about to give you that caveat. But I'm so putting the lithium aside or being optimistic, we can explain these things. But what I want to explain to you, especially the non-physicists among you, is the following. Why is it a big deal that the early universe produces helium? Because if you just look outside, what do you see? The sun. What does the sun actually do? It produces helium. So why is it a big deal that the early universe is producing helium when you see it going on every day? Well, here's the reason. The answer is in scale. The amount of helium produced during this 3-minute window processes about 1/4 of all the protons in the whole universe into helium. All of the stars in all of the galaxies over all of time to date have processed another about 2% of those protons. So the amount of nuclear processing that went on during this first 3-minute window is enormously larger, by more than an order of magnitude, than all of the stellar evolution that has taken place since. And that's why it's a big deal. It's like you're taking all the stars in all the galaxies of over all the time and putting it into one little explosion that lasts 3 minutes. So it is a big deal. There's an enormous amount of energy generated in a window. So, after 3 minutes, the universe expands more or less normally, more or less slowly, and more or less uneventfully until the universe is about 300,000 years old. And this takes us to the end of the Primordial Era. So, to summarize, we have the Big Bang, we have inflation, we develop asymmetry of matter or antimatter. Quarks get confined into protons and neutrons. We set the abundance of dark matter. Protons and neutrons produce helium. And then the micro background freezes into its thermal form, and the universe continues to expand. Now, most lectures on cosmology end about here. So I'm going to keep going. Now, we're not quite done. You've already seen maps of the micro background. This is a picture of the universe that was about 300,000 years If I made this to scale, it would just be one color. So these little fluctuations you see are about 1 part in 10 to the 5. So I had to subtract out this background. Well, I didn't, but the people who made this had to subtract out the background to give you this nice picture. So what happens is that these little tiny things, 1 part in 10 to the 5, which are probably produced by inflation during the first 10 to the minus 35 seconds, these little fluctuations in temperature of the background represent fluctuations in density of the background universe. And they grow. And if you do a simulation of the large-scale structure of the universe, they grow into this cosmic kind of structure. The scale of this is kind of about halfway across the observable universe today in spatial scale. Now, I like this picture a lot for one reason. When we do general relativity to write down the equations that give us the expansion of the universe, we assume that the universe is homogeneous and isotropic, in other words, smooth. That way we can do the math. In fact, doing that actually works remarkably well. You get 2 little simple equations which give you a huge amount of physics as you sort of see all over. But then you look in the sky and you see the universe looks completely lumpy. So it seems to be a contradiction that you can get away with this smooth approximation. But when you actually look at the universe of a large enough scale, guess what? It looks pretty smooth. Just take off your glasses and look at this picture. It's pretty smooth. Right? But nonetheless, there are lumps here. And these lumps will grow locally. And what they will do is they will grow into clusters of galaxies, ones that we can see with our telescopes. This is a Hubble telescope picture of a cluster of galaxies. And inside those galaxies, or inside those clusters, the galaxies will interact. And inside those galaxies, inside the galaxies, you see star clusters. Does anyone know what this is?
It's a Pleiades.
Ah, very good. You can see this with your naked eye if it's clear. It's clear here more than it is back in Ann Arbor. So you guys have an advantage. And then around some of those stars, there are planets. So this takes us up to the present epoch. So what we want to do now is we want to take all of our knowledge of both physics and astrophysics that we've learned by studying the past history of the universe and just ask the question, well, the universe isn't going to stop. The equations of motion that describe all of these things aren't going to change, or at least not too rapidly. So what can we say about what happens next? And that's what we're going to do for the next 8 or so hours. No. See if you're awake. So, as you've heard, one of the triumphs, I think, of the last decade is that we finally think we know what's in the universe. So there's background experiments, there's cluster mass experiments, and there's supernova acceleration experiments. And they jointly tell us that the universe is about 30% matter, 28%, depending on what the low number, and the other 2/3 will be in dark energy. And because we're dominated by dark energy, but only barely, the universe will accelerate in the way that I told you about earlier. But because we just started, or because we're only barely dominated by dark energy, we're just barely starting to accelerate. So, what I'm going to show you is a movie of the large-scale structure of the universe forming. The counter in the lower left gives you the size of the universe in units of phase value. So the early part of the movie is boring, so I've skipped to the good part where the universe is about 1/4 the size it is now. And I'll show you this. So just watch it and then see, here we go. This is going to zoom in on the largest cluster in the universe. And you see I'm forming a cluster. And then right now you notice that the counter has passed 1 because I was too lazy to turn off the computer. So it's expanding, or it's calculating what happens into the future. Now, like many movies, the ending becomes pretty unsatisfying. Because ain't nothing happened for the last half of the movie. There's a reason for that. Remember, the universe is starting to accelerate. In the fairly near future, the universe will accelerate a lot. And that will basically isolate every bound structure in the universe today. So you can see that by looking at stills from the movie. So here are the stills. If you look at the universe today, where it says 14 big years, I've rounded up, you see these web of structure like you've seen many pictures of before all week, right? But if I look at the next panel, little red square on the top, it's the whole panel below it. You see that in only 92 gig years, each halo becomes its own isolated island universe. Now, I can't emphasize this enough. It's not just that they're really far apart from each other, but the halos are far apart from each other and accelerating away from each other in this disconnected mode, so that they will not even be able to send light signals to each other. So, you spent the week learning about the Big Bang. And let me make this point, and I'll take a question. So, one of the things that I hope you took away from these great lectures you heard this week was that there's really at least three pillars of the Big Bang. There's the cosmic expansion, there's Big Bang nucleosynthesis that we just talked about, and there's the cosmic microbackground. And those three experimental things give us confidence that there really was a Big Bang, and we know what we're talking about when we talk about the Big Bang. Now, imagine that you're in this little island universe 100 billion years from now. Can you see any of those three pillars of the Big Bang? Well, since you can't see anything outside your island universe, even though the universe is expanding, there are no markers to tell you it's expanding. So you might not know the universe is expanding. The microwave background will redshift. And if you wait long enough into the future, it will redshift to the point where the wavelength is bigger than your galaxy, and then you won't be able to measure it anymore. So you won't be able to see the background anymore. And finally, if you wait long enough, stars are producing helium. It's possible for them to produce so much helium that you won't actually see the primordial production of it that we see today. So if you wait long enough into the future, you could actually lose the three pillars of the Big Bang that you guys spent studying. Let's take a question.
Are these island universes the size of supercluster halos or like local group halos?
Oh, well, the story is that for each bound structure, there will be an edge such that beyond that edge, everything gets accelerated away. So each bound structure in the universe today will go through this evolution and become its own island universe. But there will be some, like the movie I showed you, is a 10 to the 15 solar mass, even bigger than Virgo cluster. But our own local group will do this too, or the local group is Milky Way and Andromeda. So this will happen for each size cluster, whether it's a little local group or a big mega cluster. Yes?
A couple of the lectures suggested that, I just want to get some chronology straight. A couple of the lectures suggested that the inflationary era actually happened before the Big Bang. And it sounds like you're saying it happened immediately after the Big Bang, which is...
Oh, that's a good question, and it depends a little bit on which you believe. I defined the movement of the Big Bang to be at a time scale of 10 to the minus 43 seconds, because that's the quantum gravity scale. What we really know is that the universe was accelerating up until about 10 to the minus 35, 36 seconds or so. So it is possible that whatever event that I was vaguely talking about that brought the universe into existence, that event could include inflation. So the universe could be separated from its original space-time manifold with an inflationary event. I think the fair thing to say, different people will give you different answers to this, but I think the fair thing to say is that we're still working out what the correct answer is. The deal with inflation is that there are many scenarios that can be made to work. So it's not a problem of getting it to work so much as a problem to figure out which one is the right one. Right? Anthony wanted to comment.
Yeah, I wanted to complain more about the terminology there. 'Cause
Okay.
I think there's I think it's important to differentiate between what we know a lot about, which is that the universe had this hot, expanding, uniform era. So the Big Bang model that came from say, pre-nucleosynthesis up till now, that's extremely well tested.
Right.
And happened. And then there's an epoch before that which probably included inflation. If you believe certain people may well have included eternal inflation, which is a potentially infinite or an arbitrarily large amount of time. And then there may or may not have been, in my eyes, a cosmological singularity. There may or may not have been a single event or many. So it becomes much more ill-defined.
That's all true, yes.
I've been getting increasingly frustrated with using the term Big Bang both for the cosmology that we know happened and is totally under control, and for the putative initial singularity, which may not have happened, and certainly we don't know much about it.
And the singularity is certainly not singular because it's washed out with quantum effects, right? So, yeah. So, but that's one thing. I think what you're thinking on a very important point for the audience. We use the term Big Bang in two completely different ways. One is what I call the Big Bang moment, correctly or incorrectly. And second is what we call the Big Bang model, which is kind of all of the above. And we know that story from probably the weak scale on down pretty well.
Yeah.
Depends on how you are. Okay, so back to the story. So I made the point that, yes.
Sorry. So these pictures that you've got here are pictures of, if we were in that red box there, this is not something that we would ever actually see. This is sort of like this is a view from inside a simulation or something like that, right? I mean, this is, I guess what I'm asking is, so at a certain point, all of those non-balanced structures leave the horizon and you're not in causal contact with them anymore. But there's a difference between what you're in causal contact with and what you see when you look at the sky. There's going to be like old light from some of those things that still comes in.
Right, but if you wait long enough, even the old light won't get to you.
How long do you have to wait?
Just beyond this time here. Okay. So we're only a factor of 10 in time older than today, order of magnitude, right? So it's only one cosmological decade longer. And this story will go all the way up to 100 cosmological decades.
Right.
So compared to that, it's really soon. Okay.
Fair enough.
Of course, since we have 100 cosmological decades to cover, we might be here all day.
So isn't this picture contrary to what you said at the very beginning about Copernican principle for time, because our time is kind of special because we have access to Big Bang and other times don't?
Well, that's a good question. In fact, that's one of the discussion questions I have at the end of the talk for you to consider over the weekend. So you should write an essay on that and report back to us Monday. No, so seriously, let's talk about that afterwards. That's a great question. And it depends what you mean by all of those words as to whether the answer is yes or no. So but let me defer you for now, if I will. Now, I have one more point to make. If you look at the universe today, which is the top panel, and you look at one of the little lumps, which is a dark matter halo today, and you think of it as either a cluster or the dark matter halo of an individual galaxy, and you ask the seemingly sensible question, what's the mass of a galaxy? The answer is we don't know. Now, there's a reason why we don't know. The reason we don't know is that galaxies, halos, aren't quite done being formed. So we don't know where to draw the boundary between what's going to be in a galaxy and what's not going to be in a galaxy. And the reason is simply that the universe isn't quite old enough for us to answer that question. But by doing this exercise of studying the future universe, we can start to get some information on that question. So the cosmologists know this, of course. They're very clever people. So since they can't define the mass of a galaxy exactly, they have defined a series of mass proxies for galaxies. So let me give you one of them. If you take a sphere, such that the mean density of that sphere is 200 times the background. Then you take the mass enclosed within that sphere. You call that mass scale M200, where M stands for mass and 200 times stands for the fact that the density in that sphere is 200 times the background. That quantity is well defined. And it gives you an idea of what the mass of the object you're talking about is. Now, cosmologists have done 1, 2, 3, 4, 5 of them. These are 5 mass proxies plotted as a function of scale factor. So if you look today, you get a value. But if you look a little bit in the future, you get a different value. But the nice thing is that all of those values flatten out with time. And it's also true, from the skills that I showed you on the previous picture, that the radius of a galaxy will actually develop a well-defined edge shortly into our future. So if you believe the physics that does these simulations, we can actually define the mass of the galaxy by going into the future. So what I'm showing you here is the NFW profile, which you might have heard about, a Herdquist profile, and a truncated Herdquist profile is plotted on top of a stacked representation of all the halos in the simulation that I showed you. The point is simply that if you wait into the near future, all of the halos develop in universal form. They have a well-defined edge, and they have a well-defined mass. We can call that the asymptotic mass. And here's the cool thing. There's a similar relationship between the asymptotic mass that a halo will have and M200, which everybody uses as a stand-in for mass. The difference between them is a factor of 1.95, or about 2. So the real mass of the galaxy is about twice M200. So, why is this good? This tells us that by studying the future of the universe, we can actually define the mass of a galaxy. Today, we know how much, on average, how much stuff in that messy picture in the previous case, how much stuff will come inside the galaxy and how much will be carried away by the Hubble field.
And in this case, the galaxy means Milky Andromeda.
Yeah, the joint halo of the largest bound structure, yes. Good point. So anyway, that's kind of cool. Now, let's actually look inside the joint structure of our Milky Way and Andromeda. Now, one of the cool things is that we are living in a small local group of galaxies, where we have one big galaxy besides ours in Andromeda. The other interesting thing about Andromeda, which you may or may not know, is that it's actually headed straight for us. Okay? So in about Hubble time, Andromeda will collide with the Milky Way. So the beautiful spiral patterns that we think we see in our galaxy, it's hard to see them again, and the ones we see in the spiral in Andromeda, they will be completely messed up in a train wreck in only about a Hubble time. Now it's possible that we can't measure the velocity vector of Andromeda exactly, so there is a chance that in a Hubble time, it won't actually hit the galaxy, our galaxy, it will come by it. But they're still bound, and that means that one Hubble time later it will come back and smack it, so it doesn't really matter. So now let's ask the question. Suppose you can live for 10 million years, or 20 million years, and you can witness this collision not from the outside, where you see these beautiful but destructive streamers reaching down the galaxy. But suppose you could view it from within. What would you see? Think about it this way. If you shrink stars down to the size of grains of sand, then the space between those stars is a couple miles. So imagine that your friend is a couple miles away with his grain of sand, and you've got your grain of sand, and you're going to try to throw it at his grain of sand. Chances are you're not going to be successful. In a similar way, when Milky Way and Andromeda hit each other, chances are good that no two stars will actually collide. And that's because the galaxy is actually relentlessly empty. So if you could live for this 10, 20 billion years and see the collision, what you would see is basically a doubling of the brightness of the night sky. So it would be a very gentle collision when viewed from within, even though it's a very violent collision when viewed from without. Yeah.
Are the distances between stars much smaller in the center of the galaxy?
Oh, yeah, I'm only talking about the field.
Okay.
So if two star clusters smash into each other, you could in fact have some collisions. But in the field is empty. The numbers I gave you are for the field. In fact, given the age of the universe today, chances are good that no two stars in the field have actually collided to date. The galaxy is just relentlessly empty. And that's one of your many lessons for today.
And saying that the night sky will just brighten up a bit, that's assuming that we don't get shut off from one of these tails, right? If we get on the tails, then we get this nice view of the galaxy. But would that be sort of a, like, how many of them get shut off from the tails, you know? And if they do get shut off from the tails, is there a lot of acceleration associated with that too? Would that be uncomfortable, or would it just be a different view?
You asked a lot of good questions there. Exactly how much gets stripped out in the tail depends on the exact parameters of the collision. And it also depends, you're more likely to be stripped out in the tail if you're in the outer part of the galaxy. We're sort of only 8 kiloparsecs from the middle, so we're a little bit unlikely to be stripped out, but never say never. Your other question about it being uncomfortable is that all of these things play out on timescales of a Hubble time. So you won't notice it, right? It's not going to be some violent collision where you're stripped out and you would feel the acceleration like you do when you break into your car, right? It's going to be so gradual you just wouldn't notice it. Now, after the fact, if you end up like here, you would have a beautiful view of the rest of the galaxy. And that would be nice.
You also would have a lot of gas and dust interacting, so, and that presumably would collide or heat up or something, so you'd have something else going on besides the stars colliding, right? I mean, how would that play out? You just have a more glowing sky, or?
Oh, well, you raise a very good point. I wasn't going to talk about this, but since you asked it. Most of the gas that's ripe to do anything lives in molecular clouds. There's other gas between clouds, but the gas in molecular clouds is most important for your question. And if two clouds collide, and they will, not a lot, but some of them will, you'll get a burst of star formation. And the reason it's actually pretty easy to understand, because the clouds are held up in magnetic fields. And imagine that you have a magnetic field pointing in this direction, and this cloud, and this direction, and this cloud. If I collide them like this, the mass to flux ratio stays the same. But if I collide them at any other angle, I short out some of the field, but I have twice the mass. That will give me relatively more action for star formation. So, what we see in the universe today is that when galaxies interact, some of them become what we call starburst galaxies, which means they're bright in the infrared and they have a lot of star formation. So this won't happen in our galaxy in Andromeda for another Hubble time or so. So there won't be that many molecular clouds, but we will get a little bit of extra star formation from this effect. So if you're near such a star-forming environment, it would be in fact quite dramatic. And it would be very nice to see. Yes.
So, jumping back to the long-term future of galactic halos. So, let's say you imagine that dark energy is not constant, but it actually increases in the future. Is there a critical value greater than the value today that would actually unbound some of these gravitational structures?
Yes, if that's a huge if, of course, because it violates the strong energy principle of GR. But if you can do that, then once if you can have an increase in vacuum energy, and it continues to increase, it will actually unbind everything eventually. And then you're just, everything in the universe will be ripped apart, and that will be the story.
It's known as the Big Rip.
Yeah. You know, it's important to have names for everything. Okay, so let's now ask what happens a little bit closer to home. What happens to our own sun in the future? So here I'm showing you an HR diagram, a Hertzsprung-Russell diagram, to remind you astronomers plot power or luminosity on the vertical axis, and they plot temperature or spectral class on the horizontal axis. Now astronomers do everything backwards. So the hotter stars, the higher temperatures, are on the left. That's just the way they do it. So when a star has a certain configuration, we'll live at a certain point in this diagram. So right now, the sun lives at point A. And if you go over here, it has a luminosity of 1, which seems like a nice coincidence to realize that we're in units of solar luminosity, so it's by definition. Now, as the sun evolves, it will get brighter. And as it gets brighter, it will change its temperature and its power. So, in about 3.5 billion years, the sun will move from point A to point B. Now, I know you're all saying, well, so what? Well, that movement in the HR diagram spells the end of life on Earth. Because the sun's only 40% brighter. But that's enough to drive a runaway greenhouse effect on the Earth, probably boil the oceans, probably sterilize the biosphere. And probably the longest we have before the biosphere is compromised is 3.5 billion years. It could happen as soon as 2 billion years, depending on whose projection you read. But we have billions of years, but only a couple billions of years. And point B is plotted for 3.5. Now, if you're Earth, not a person, but Earth, you don't actually care that there's people on the surface of your planet, right? Earth as a planet doesn't care that we're here. It will survive this little epoch without any problem. However, in about 7 billion years, the sun will move up to point C. Then it will be about 10,000 times brighter than it is now. And its outer surface will be where the radius of Earth's orbit is, will be in its full red giant phase. At that point, the Earth as a planet is in peril. And I'll say a few more words about that in a minute. So, what will happen is that if the sun were not losing mass, then the outer surface of the sun would encompass the radius of Earth's orbit, and it would eat it directly. But the sun loses mass as it expands, and as it loses mass, the radius of Earth's orbit slips out to a larger value, but not fast enough. It's kind of a little bit of a dicey race as to whether the Earth gets eaten or not. But most projections suggest that it will. In addition, there's frictional forces, mostly due to tides exerted on the Earth by the squeezing of the sun, which will make the orbit decay and drag it back to the sun. So most projections suggest that life ends in 3.5 billion years. Earth itself will end in 7 billion years, all due to the warming of the sun. Now, with that cheery prospect in mind, there's hope. So I have a little scenario for you where a red dwarf saves the Earth. So it turns out that I told you collisions are rare and the galaxy is rather empty. But it's possible for stars to come by and liberate the Earth from the solar system. Most stars are red dwarfs. They don't quite look like that, but that's what you get when you use the internet. Most stars are red dwarfs, so if stars were to wander through our solar system, chances are good they would in fact be red dwarfs. So here's a simple scenario where one red dwarf comes in, and the sun, the moon, the earth, and the red dwarf all go in different directions. You can have a whole host of scattering interactions like this. Here's the typical one, which means it's the coolest one I got. And here you have a red dwarf pair coming in to interact with the sun and earth. And it's a resonant interaction. So instead of just one flyby, the four bodies orbit each other for 9,000 years. And what happens during that 9,000 years is that red dwarf binary pair comes in. The sun gives the earth to one member of the pair, who gives it back to the sun, who gives it to the other member of the pair, who then leaves the dance with the earth in habitable orbit. Now, the Michigan has long winters. So I've done about 1 million of these flyby simulations on my computer. There's not a lot to do, you see. So what we can do with all these results is we can count through them and calculate either cross sections, the effective area a solar system has for this kind of event, or we can calculate probabilities that this will happen over a certain amount of time. So you see that I can save Earth in 2 ways. I can save it by injecting it from the solar system, or I can save it by capturing it via a passing star. And we have 3.5 million years before life on Earth ends, so I'll use that as my time scale. So the odds of Earth being saved by being ejected are about 1 part in 10 to the 5. The odds of Earth being saved by being captured, this is one process, is about 1 part in 3 million. Now, 1 part in 3 million is about the same odds as you winning the lottery when you go buy a lottery ticket. Just to put that in perspective. Now, there's a couple things that we need to talk about here. One is, what good does this do us? Well, this same kind of calculation, let me finish this thought first. The same kind of calculation can be used for solar systems today. So in addition to the cases where I studied the solar system with Earth and the sun in the field, you can also study solar systems in stellar clusters. And we can calculate the cross sections for changing solar systems in stellar clusters. And this is important because most stars are born in stellar clusters. So I can calculate cross sections for increasing the eccentricity of planets, for ejecting planets, for capturing planets. And all this takes place in clusters today. Now, I have a whole different talk I could give, but I won't. But you can use these kinds of pieces of physics to put constraints on the birth environment of our own solar system. Because we know that our solar system formed in a cluster, but we also know that our planetary orbits are very well ordered. They have low eccentricity, low inclination, and low, in short, they're not messed up. And because they're not messed up, we knew that we had limited interactions. So once you calculate the cross-section for the interaction, you can then put constraints in the history, the dynamical history of our own solar system. So, once again, studying the future of the universe leads to pieces of physics which can be used to study astrophysics in today's universe. Let me take your question now.
So you mentioned these couple scenarios that could save Earth. If you're, and these are possible but very unlikely. If you're a super advanced alien civilization or super advanced Earth, what would be the best way to change Earth's orbit in order to save Earth in that way?
Well,
if not trying to aid these other mechanisms.
well, I'm not sure that I would know the best. Well, I'll give you 2 thoughts, okay? I'm not much of a futurist when it comes to life, so take that in mind as I answer your question. But it seems to me the simplest thing, instead of trying to move a planet, is to just build a spaceship, make it like an ark, and go out and have your own little ark, right? That would be sort of the cheapest way. However, if you want to save Earth, because you're partial to it for who knows what reason, maybe you want to save the dolphins or the humpback, but that's what it's doing. Here's how you do it. The problem is that the sun is getting brighter as it ages. So you have to move Earth out to a larger orbit. So with people here at Santa Cruz, Corey Kansky and Greg Lawford, who's now the chair here, we did a little calculation where we put an asteroid in orbit, where it comes by the inner solar system every 6,000 years. And when it comes near the Earth, it does a gravitational assist interaction to it, so it moves Earth to a higher orbit. And if you do this every 6,000 years, it turns out that every 6,000 years, Earth and Jupiter and Saturn are basically lined up. So by tuning the orbit carefully, the asteroid can give energy to Earth's orbit, making it a higher orbit, farther from the sun. And it will regain its energy and angular momentum from Jupiter and Saturn on the way out. Presumably, you might have to tune it at astron or at helium a little bit to get it exactly right. Then it can come again 6,000 years later. And it turns out that if you do this with a 10-kilometer-sided asteroid, like the one that killed the dinosaurs, you give enough boost to Earth's orbit that you can move it out fast enough as the sun gets brighter to compensate. So you can extend the lifetime of Earth's life-giving phase substantially by this astronomical engineering. Now there's a little bit of a problem in that you have to know what you're doing, because if an asteroid comes too close to the Earth, hits the atmosphere and spirals in, it would kill the dinosaurs again, which would not be good. The other problem is that you have this event every 6,000 years, so humanity would have to actually have a plan that lasts 6,000 years. We can't, at the present, we can have a plan that lasts 6 months. If you've read a newspaper in the last couple of years, you know what I mean. So we would have to change our ways a little bit to do this.
Certainly the future of life is the most uncertain part of all this. But I guess I'm asking the question to maybe temper a little bit of the pessimism about, in 3.5 billion years, that'll be the end of life on Earth, for example.
Yeah, well actually, there's another interesting point, which is what I was going to bring up next. Suppose you do eject Earth. What will happen? Well, the oceans will freeze in about 1 million years. And you might think, well, that's it, right? Well, the thing you don't know, or you might have forgotten, is that this Earth has an internal energy source. There are long-lived radioactive elements, potassium-40 and uranium deep underground, and that gives the Earth an energy source. It's about 10,000 times less powerful than the energy we get from the sun. So our biosphere is driven from that. But if you eject the Earth, that's all you got. So, if you go deep enough to the Earth with just this internal energy source and no sun, so an ejected planet, you will have liquid water pockets deep underground. How deep? 40 kilometers is the magic number. So, if you eject Earth from the solar system, life will actually last longer than if it stays. Because if it stays, we're sterilized in 3.5 million years old. But if it goes, you have little pockets of water and extremophile bacteria for 30 million years. You're still toast, so that's right, but life itself will last longer. Now, one thing that is interesting that if you follow this idea a little bit further, when you ask the question, where is most of life in the galaxy or in the universe, since we've all grown up on Star Trek, we know that it's on Earth-like planets where they speak English. Right? But if you think about it, it's actually kind of rare for Earth to have 4 kilometers of water on its surface. And the reason is that you're making Earth where there's no ices on the rocks that made the planet. If you were to make Earth in the outer solar system, and I'm showing you the 4 Galilean satellites here, then there's ice on the rocks that make the bodies. So you naturally get lots of water. Each one of these has an ice layer that's 100 kilometers thick, which is bigger than 4. So suppose you were to make an Earth where Jupiter is. You would expect it to have 100 kilometers or more of ice. It would still have its internal radioactive source. So you would have frozen ice on the outside, liquid water down to 14 kilometers, or at 14 kilometers, a little less depending on the external energy. You would have liquid water there. So the most common environments that have both energy and liquid water are actually on frozen planets, not on planets like Earth, where the water's unfrozen on the surface. See, the beauty of this is that an Earth-like planet with ice and an internal energy source can be anywhere. There's no Goldilocks problem of habitability anymore. It can be anywhere. So the most common places for life are probably on frozen planets, not on habitable planets, or what we now call habitable planets. That might not do you a lot of good if you don't move them, but if you ask where all of the life is, that's where the answer probably is. Now there's a little bit of support for this idea in that some theories suggest that life on our own Earth actually developed deep underground without sunlight. And if that's the natural way for life to evolve everywhere, then these frozen planets across the galaxy would be teeming with life. This is, of course, a little bit speculative. So let's move on. Going back to the big picture, the galaxy is continuing to make stars, as we talked about, but it's going to run out of gas, quite literally. Stars are made out of hydrogen gas, and will continue to make new stars until we literally run out of gas. So when will that happen? Well, if you take the current star formation rate and the current amount of gas, and you just divide them, you get a time scale, which is only a few multipliers. So if nothing else happened, you would run out of gas in 10, 20 million years. However, these time scales are lengthened because stars return some of their mass to the inner stellar medium. The galaxy is actually continuing to gain some gas by infall, but mostly, as the gas supplies dwindle, the star formation rate goes down. So the galaxy naturally practices conservation, right? So that will keep the star formation rate going for a while. Now, if you turn all the knobs to one side, the longest the galaxy like ours can sustain normal star formation is about 10 trillion years or so, or tens of trillions of years. So once the galaxy becomes older than about 14 cosmic decades, it will run out of material to make new stars. Star formation will ground to a halt. And what that means is that if you look at the universe on time scale longer than this, all you get are the stars that you already have. So the $1 million question becomes, how long do the stars last? Now, for those of you who are not stellar astronomers, let me remind you that stars of different masses live for different amounts of time. A star like the Sun with one solar mass will live on average, or in rough terms, 10 billion years, which is close to the age of the universe. A star with 10 times the mass of the Sun will only live for 10 billion years. That's a big difference. But a star with a tenth of the solar mass will live for trillions of years. So here, I'm showing you another HR diagram. This was done with Greg Laughlin and Peter Bodenheimer, we're also here at Santa Cruz. This shows you the tracks of the low-mass stars over trillions of years' time. And you see a whole bunch of interesting things here, so let me put them out to you. Again, I'm plotting the power on the left side and the temperature on the bottom. And the temperature is plotted backwards, keeping with astronomical tradition. So, if I look at the smallest stars, they get bluer and they turn over and become white dwarfs. The smallest stars don't become red giants. Remember, the Sun does become a red giant. Now, it turns out that in astrophysics, we know that the Sun will become a red giant. We can see red giants in the sky and piece together observationally what stellar evolution should look like. We can also build computer codes which will tell us a star will become a red giant. But if you ask someone to go to the blackboard with basic equations and tell you why a star becomes a red giant, it's actually hard. But you see, here we have an opportunity to study the problem, because the 20.25 solar mass star does become a red giant. It's going to pop and will turn over and be red. And these stars become blue and don't become big. So on Monday, I'll tell you how stars work and how they become red giants. But what I want to emphasize just for today is that by studying the future, by studying small stars, some of which don't become red giants, we can actually learn something about how stars do become red giants in our universe today. The other thing that's interesting is that if you look at this track of the 0.16 solar mass star, you see it has a long extended period when it has a nearly constant luminosity. The constant luminosity is about a third of that of the Sun. which is a lot of power. And the length of time over which it's flat is about 4.6 billion years. Does that number sound familiar? Well, at least in our own case, Earth was able to develop life and get all the way to people in 4.6 billion years. So if there's any planets around these stars, trillions of years from now, they can come out of cold storage and be warmed up, and they can enjoy an extended 5 billion year time when they're being exposed to a similar kind of radiation exposure. Since the power is down by a factor of a couple, light would have to be slightly closer. But otherwise, it would be just the same scenario as Earth, only trillions of years into the future. Which is kind of interesting. The other thing is that if you look at the inset diagram, it's hard to see, so let me blow it up for you. You see that the time is measured in trillions of years. So the smallest star is the one that's lived the longest. And for this case, where we have the mix of heavy elements that the sun has, the longest lived star will live for 12 trillion years. This number should also be familiar to you. Because remember, we asked the question, how long can a galaxy like the Milky Way sustain normal star formation? And the answer we got was tens of trillions of years. Now we've asked the question, how long can the longest lived star last? And the answer is tens of trillions of years. Those numbers sound similar, right? So that gives us the following picture. Oh. It tells us that star formation rates and stellar evolutions are sort of synced up. We've also seen that the low mass stars get brighter as they age. So the hot mass stars die because they live for a little bit of time, but their energy is replaced by the brightening of the low mass stars. So if you look at the total power output of the galaxy over time, it's damn near flat for a long time until star formation starts to peter out. And then you have this plummet velocity. And that won't happen for trillions of years. So you see that because star formation and stellar evolution both kind of have maximum time scales of tens of trillions of years, in a logarithmic sense, there's a rather sharp transition, a rather sharp end to the Astrophysics era. So when the universe is less than Cosmological Decade 14, it will be bright, have lots of stars, there'll be lots of energy generated. But when the universe is older than 14 cosmological decades, there'll be no more normal star formation. And there will be, and the longest lived stars will die off. So we make a rather sharp transition from a universe with stars to one without. I'd also like to emphasize here that by studying the future, we learn a lot about astronomy today. We learn why stars become red giants. We learn why dark matter halos have their forms. We know how to define the mass of a galaxy. There's also some other dynamical things that I haven't had time to talk about. But all of these pieces of physics that show up in understanding the future of the universe can inform astrophysics of today. So now we're an hour and a half into the talk. We've covered the first 2 of the 5 eras. We're in pretty good shape. Let me just skip that. So, when the universe becomes older than 10 to the 14 years old, the stars are gone and they're replaced by the remnants. So let's take a moment to take inventory. What's in the universe in the future here? Well, we have 4 things: brown dwarfs, white dwarfs, neutron stars, and black holes. Let me remind you what those are. Now, most stars, if I define a star to be something that would convert hydrogen, most stars will turn into white dwarfs after they die. So every star from a mass of 0.08 solar masses to 8 solar masses will turn into a white dwarf after it dies. Now you can ask, well, what percentage of stars are in that mass range? And the answer is 997 out of 1,000. Is, in other words, almost all of them. So everything that you think of when you think of a star will really become a white dwarf. So why do I have 3 other things on the board here? Well, when you make a star, the material doesn't know in advance that it has to have at least 0.08 solar masses so that it can burn nuclear fusion, because nuclear fusion does not actually play a role in the formation of stars. So as a result, we make a lot of failed stars that we call brown dwarfs. These are objects that have less than 0.08 solar masses. Now they're still around in the degenerate era. Why are they degenerate? Well, the reason why they haven't burned their hydrogen is because they're degenerate. Degeneracy pressure keeps them from getting hot enough to undergo nuclear fusion.
Actually, I think you better explain what degeneracy pressure is.
Oh, okay. Well, right. All right. In quantum mechanics, there's something called the uncertainty principle. And it tells you that the uncertainty in position and the uncertainty in momentum cannot both be small. The product has to be bigger than something. Well, something is H bar, right? So imagine that you want to have high density material, like inside a star. Well, if the material is high density, delta X has to be small, otherwise you don't know that the star is there. So if you make delta X small, you make delta P big. In other words, as you squeeze material together, you induce an uncertainty in its momentum. And you can't have total momentum being 0 if the uncertainty is large. So that effectively gives the particles a momentum. Well, particles with momentum will exert pressure, and that pressure is called degeneracy pressure. So if you try to squeeze stellar matter too close together, it pushes back due to quantum mechanics, and that effect is called degeneracy pressure. Now, when you make a star that's too small, which is what we call brown dwarf, it doesn't have enough mass to overcome that degeneracy pressure. So it's kind of stillborn. It just sits there. It's like the ultimate stellar slacker. So it's sat around for half of infinity and it still hasn't done anything. But these things are important because they're an important source of unburned hydrogen. Now, when most stars die, they become a white dwarf. So what the white dwarf is held up by is the degeneracy pressure of electrons. So if you take something the mass of the sun and you squeeze it down to the radius of the Earth, it will be supported by degeneracy pressure. And that's loose terms for light dwarfs. Now, 3 out of 1,000 stars are actually bigger than 8 solar masses. So 3 out of 1,000 stars will have a different kind of death. They will blow up in a supernova explosion at the end of their lifetimes. And most of those will turn into neutron stars, but some of them can become stellar black holes. We think the largest stars will produce stellar black holes, that most of them are actually just over the threshold to blow up, and most of them will become neutron stars. Now, a neutron star is an object that has about the mass of the sun, squeezed into about the size of Santa Cruz. It has a radius of about 10 kilometers. And it's got a density about the same as nuclear density, so roughly 10 to the 15 times the density of U. And this is the class of objects that we have in the future. Now, by numbers, we have almost equal numbers of white dwarfs and brown dwarfs. The white dwarfs are actually about 10 times more massive. So by mass, all of the mass is in the white dwarf. Then we have this tiny sliver of neutron stars and black holes that we left behind. So, this is what's in the universe. The next question is, well, what do they actually do?
You did leave out the supermassive black hole.
Well, what's that?
The supermassive.
Oh, I'll get to that.
Yeah. But they're also degenerate.
Oh, right.
Tiny fraction of the mass.
Oh, right. So Joel's making the point that there's actually 2 kinds of black holes. There's stellar black holes that are left over from stellar death, and that's what I've been talking about here. But in the middle of every galaxy, there's a great big black hole. And astronomers thought long and hard about what to call them. They call them supermassive black holes because they're supermassive. And the inventory is such that each galaxy has one big black hole in the middle, and then a galaxy the size of the Milky Way will produce kind of sort of about 1 million stellar black holes. The supermassive black hole in the middle of our galaxy is about 3 million solar masses. So kind of comparable numbers of mass. But I'll come back to that in a bit. There are two kinds of black holes. So I told you that star formation ended, but it turns out that I'm lying to you. I told you that collisions don't take place. Turns out I lied to you again. If you wait until the universe is older than 10 to the 15 years, then it's possible for collisions to take place. They're very, very rare, but if you wait long enough, rare events can happen, right? So, suppose I have two brown dwarfs. They're not individually large enough to undergo fusion. But if I bash them together, the merger product will contain most of the mass, and the product can be over the threshold for stardom and start to burn hydrogen. So, we know, roughly speaking, how many brown dwarfs are in the galaxy. We know, roughly speaking, how fast they're going. We can do numerical simulations to show you how close to each other they have to get in order to merge. So we can put all these pieces together and estimate how many stars will be shining in the Milky Way in the future due to this process. I should also remark that when we make a star through this process, it will have a mass of about 1/10 of the solar mass, and then it will live for about 10 trillion years. So we know how long they live too. So remember, the galaxy today has billions and billions of stars, as St. Carl has taught us, right? The galaxy of the future will have 1 or 2 stars produced through this process. So imagine the dark galaxy of the future. It's billions and billions of stars in the night sky, and you have 1 or 2 of these guys. And these stars will be about 10 of the solar mass. It will be 1,000 times dimmer than our sun. And that's mostly what you get. But in addition to the brown dwarfs, we saw there's very roughly equal numbers of white dwarfs. And the white dwarfs too will collide. The problem is that most white dwarfs are small. So when most white dwarfs collide, you just get another white dwarf. However, when the biggest, baddest white dwarfs collide, the product can be over what's called the Chandrasekhar limit. It turns out that if you make a white dwarf bigger than 1.4 solar masses, then it can't support itself anymore with this degeneracy pressure we were talking about. It will blow up. So when the very largest white dwarfs collide, the merger product, much like this one, will be over the Chandrasekhar limit, and the object will blow up. So the star galaxy of the future will be punctuated every once in a while by a spectacular supernova explosion. But those will be very rare. Another process that plays a role in the following. You learned all about dark matter from Joel earlier this week. Well, the white dwarfs of the future will hoover up the dark matter particles that Joel has taught you about. If you take the typical interaction cross-section, then a white dwarf is just about optically thick to a dark matter particle going through it. So over time, the white dwarfs will collect these dark matter particles in their centers. And when the collection of dark matter particles in the center becomes large enough, they will annihilate with each other because they're their own antiparticle. And that will provide the white dwarf with an energy generation mechanism it wouldn't otherwise have. So the white dwarfs of the future will have a power source due to dark matter annihilation. Now there's some uncertainty in this because we don't know what the cross-sections are, exactly what the mass of the dark matter particle is, and so on. But in rough terms, the amount of energy generated through this process will be quadrillions of watts. Now what does that mean to you? It should mean something to you. Let me tell you what it should mean to you. If you take the Earth and you ask how much power of the sun is it intersect, that's all of the solar power. That's what drives our entire biosphere. Some fraction of that we might need to drive our civilization when we run out of oil. So what is that number? It's a very important number. That number is 100 quadrillion watts. All of the solar energy we get for an Earth-sized object is 100 quadrillion watts. A white dwarf of the future, which coincidentally has the same radius as the Earth, will have a power source measured in quadrillions of watts. But then the energy is coming from the inside out instead of being absorbed from the outside in. But otherwise, it's kind of like an inside-out lifespan. That's a good way to remember how it works, right? It's just like Earth. Because both the radius and the power radius are very similar. So we have 1 or 2 real stars and billions of billions of white dwarfs with Earth-like power sources. What else is going on? Well, I told you that stellar collisions are rare. So if collisions are rare, then near misses have to be more common, right? So what happens when stars whiz by each other and don't hit each other? Well, they exchange energy. So you can think of the stars in a galaxy as somewhat like the molecules in a glass of water. They share energy. Some get kicked up to high energy. Some get kicked down to lower energy. Those that get kicked up to high enough energy will fly away. They'll literally evaporate. So if you wait long enough, the whole galaxy will evaporate in this way. And the time it takes to evaporate is about 20 cosmological decades. So almost all the stars will actually evaporate, and only a few will fall to the middle at low energy and be eaten by the black hole that lives there. Now remember, at this time in the future, 10 to the 20 years from now, Andromeda and the Milky Way will have long since collided. So the galaxy we're talking about isn't the Milky Way or Andromeda, it's their merger product, whatever you'd like to name that. That will be another assignment for Monday, is to come up with a good name for the merger product of Milky Way and Andromeda. So now I'm going to skip ahead. The next big thing on the calendar is that the protons will eventually decay. I made the point early on in the lecture that baryon number is not conserved, so that we expect protons to decay sometime. Now, proton decay is a bit of a dicey thing, in that there's lots of different ways of proton decay, so there's a lot of channels. And unfortunately, we're in a situation where the lifetime is very uncertain. On the other hand, it is in fact science. The proton decay experiments, and there are experiments, are in their 4th generation, depending on exactly how you count generations. But we have well-defined experimental limits that show that the proton lives longer than 33 or even 34 cosmological decades. So it's actually kind of interesting that we can measure a time scale so much longer than the current age of the universe, but we can. The trick is that you want to use more than one proton. So we know experimentally that the proton has a lifetime longer than 33 cosmological decades. There's a theoretical argument that I'll give you in a minute that implies that the upper limit is about 10 to the 45 years, or 45 cosmological decades. That's not a firm argument. In other words, this slide is on very much more firm footing than this slide and this slide. But this won't stop me from telling you about this kind of slide. Now, the reason why this is important is that proton decay, when it happens, will change the universe more dramatically than just about any other process that we're talking about today. So, in some sense, you can understand a little bit about proton decay by looking at one of the channels. It happens not on the scale of the proton itself, but on the scale of its constituent quarks. So in rough terms, 2 of the quarks interact through an intermediate particle and become a positron and an antiquark. The antiquark pairs with the 3rd quark, making a pion. Well, the pion only lives for a fraction of a second and will decay into photons. So, and the positron will fly, this happens inside a white quark, for example. The positron will quickly find an electron to annihilate with, and those 2 things will then turn into 2 more photons. So, there are other channels, but many are similar. So if proton decay takes place inside a white dwarf star, you basically turn all of the mass of the proton, plus an extra electron, into 4 gamma rays. Now, the likelihood of this process happening depends on the mass of this intermediate particle. If the mass of this intermediate particle is what's called a gut scale particle, which means grand Newton scale, which means 10 to the 16 GeV, then the lifetime is about 10 to the 32 or 10 to the 33 years. This isn't a coincidence that the experiments are searching that part of parameter space, because there was some prediction that grand Newton particles would in fact drive this process. It's just so far we haven't found it. It might be just around the corner, or it might not be. Now, where does 10 to the 45 come from? Well, if you say three things, you say that gravity does not preserve baryon, and that quantum gravity produces little tiny quantum black holes. And third, the quantum black holes can act as an intermediate particle. So I got three ifs then. If I have all three of those ifs, then the time scale for this process to be driven by gravity is 10 to the 45 years. And since gravity is probably the last resort, that's why it's sort of not done. But there's three ifs in there that we have to come clean about, right? Now, in spite of the uncertainty in the lifetime, and I'm quoted as being anywhere from 10 to the 33 to 10 to the 45 years, in spite of that uncertainty, once you've picked a lifetime, the evolution is actually pretty well defined. The only difference is what scale I put on my clock. So I'm going to show you some plots. Here's a movie that shows the evolution of a white dwarf. It's a half a solar mass white dwarf, which is exactly like what the sun will turn into. So this is, if you will, the evolutionary diagram that shows the long-term fate of our own sun. Now, I had to pick a proton decay time. So this is done for 10 to the 37 years, which is sort of intermediate between. It's like the logarithm of the mean of the range I gave you. But if you change these axes, it's all the same. And since you're not going to remember the axes anyway, you don't care. So I'm going to show you the movie. So it's going, the camera shows how old we are. Now the white dwarf is green because it's degenerate. If you look carefully, there's a yellow skin on the edge of it. And that's because the outer layer is non-degenerate. It's not dense enough for this quantum degeneracy pressure to play a role. And you see that the green thing is getting bigger. As the white dwarf loses mass, it gets larger physically. So remember, it started with the mass of the sun, or half the sun, and the radius of Earth. Now it's getting bigger and bigger and bigger and bigger, and it's greener and greener. And watch this. You see it's developed a well-defined yellow skin. That means the outer layer is now manifestly non-degenerate. And look at how big it is. How big do you think it is? It started with the radius of Earth. How big is it now?
About 3 times that.
What object would you say?
Neptune.
Not bad. It's actually, it reaches a maximum radius of about Jupiter. And you see, the yellow bit has just become very pronounced. When I click it again, it will become all yellow. And you see that when it went from green to yellow, it turned the corner. It turned the corner in the diagram. So what's happening is that while the object's degenerate and losing mass, it gets bigger and bigger till it's about the mass and radius of Jupiter. Jupiter, it turns out, is just on the border between being a degenerate star like a brown dwarf and being a rock. It's a gaseous rock. The difference between a rock and a degenerate star is that when you take mass away from the degenerate object, it gets bigger. But if you take mass away from the rock, it gets smaller. So the largest the star got was at that corner. And then it loses radius and mass until it goes away to nothing. The end point is when it's optically thin, so that all the proton decay products just leave the star without interacting. Then it's not even a star anymore, it's just a little chunk of hydrogen ice. I should also remark that the composition started some combination of carbon and oxygen. And as the protons decay, you cascade these similar elements, so that by the time you're down to the mass of Jupiter, it's almost all hydrogen. And this will happen not only to our sun, but to 997 out of every 1,000 stars in the sky. And this is the long-term fate of almost every star in the sky. Now, I can show you this still. This is actually a still not from that movie, but from a parallel movie. This diagram was made with a different proton lifetime. Instead of 10 to the 37 years, I used 10 to the 45 years. But you see that you couldn't tell the difference if I didn't tell you, because you probably don't remember what the axes were. So here's the pictorial representation of what we just talked about. And the reason why I want to put this up is twofold. What happens to the neutron stars? They're going to be on a parallel track. The neutron stars start with a radius of 10 kilometers. And as they lose mass, they get bigger too. But once they get to a mass of about a tenth of their starting mass, which is about a tenth of the solar mass, the neutrons no longer want to be neutrons. They want to be protons and electrons again. So something's got to give. And we actually don't know what happens. Either the whole thing will explode, or the whole thing will just expand and become a white dwarf. So the neutron star track is parallel to the white dwarf track at this point. Then it branches. It either explodes or it jumps on to the white dwarf track. And just for fun, you can also put black holes into the same diagram. So whereas the white dwarfs are getting dimmer, losing mass as they lose mass, the black holes, which are also losing mass, become brighter. And they evolve upward in this diagram, as shown by the lower track. It's also kind of an interesting curiosity. If you plot, or if you ask, well, what physics do I need to understand the Hawking radiation track, this diagram, you think of black holes as being exotic and Hawking radiation as being hard, and both of those things are true. But we actually know the physics of those two pieces of physics better than we know stellar evolution. So I can actually give you a higher confidence rating on my black hole track than my other tracks, even though they're much more exotic. So once the protons decay, I'm kind of out of business when it comes to degenerate objects, because all of the degenerate objects are made protons. So we started with dwarfs, white dwarfs, neutron stars, black holes. We've seen that star formation continues to run dwarf collisions. White dwarfs shine by intercepting matter particles and radiating their annihilation products. The galaxy will evaporate. Black holes will get larger. And all of this good fun ends once the protons decay. And we understand everything pretty well, except for one very, very, very important number, namely, what's the proton lifetime? So if there's one thing that we would like to know, one experiment we'd like to do to really nail down the future projection of the universe, it would be, what is the proton lifetime? So, after protons decay, I enter into the black hole era, where black holes are the brightest things in the sky. Now, as we said earlier, every galaxy has a supermassive black hole in its center. The mass of those supermassive black holes are anywhere from 1 million to 1 billion times the mass of the sun. Our own galaxy has a rather wimpy specimen. It's about 3 million solar masses. But many nearby galaxies have black holes up to 1 billion solar masses. But you basically get one per galaxy. Then, as again we've already talked about, each galaxy will produce a whole collection of stellar mass black holes from stellar death. And in rough terms, each galaxy besides the Milky Way will produce about 1 million of them. Now, what is the mass? The mass of these will be 10, 20, 30 solar masses. And the reason is that stars need to be at least 8 solar masses to blow up at all. But the ones that are only 8 or 10 tend to make neutron stars. So the ones that leave behind black holes tend to be 30, 40, or 50 solar masses. And that means a good fraction of that mass will end up in black holes, so the black holes you produce are 20, 30, 40 solar masses of black hole. So they're not one solar mass black holes, they're more like 10 or 20 or 30. And we don't know. We don't know exactly what that transformation is. And basically, that's all you got. Now they shine through Hawking radiation. So I thought I would take the liberty of giving you a poor man's derivation of Hawking radiation. So if you want to understand Hawking radiation, you have to keep three things in your head at the same time. Okay? So the first thing you have to keep in mind is that there's such a thing as a tidal force. As we stand here on Earth, your feet are closer to the center of the Earth than your head, right? That means that the Earth is pulling on your feet harder than your head. And that means it's stretching you out. Can you feel it? No, you can't. Because the size of the effect for Earth is actually pretty wimpy. It's much less than whether you have a hat on or something like that, right? But near the event horizon of a black hole, we're talking about extreme gravity, so it becomes very important. So there is a tidal stretching effect. Then the second thing you have to keep in mind is there's quantum mechanics. That means because of the uncertainty principle again, I can never specify that space is empty. It's always possible for particles that shouldn't be there to end up in existence and then go away. As long as they don't violate conservation limit too long, I can have this concept of virtual particles. So, loosely speaking, when a virtual particle is in existence, the tidal force can do work on it. So the third thing you have to keep in mind is that work is equal to force times distance from freshman physics. So if you put those three things together, virtual particles come into existence, tidal force does work on them according to that formula. If you do enough work on the particle, you can promote one of them from virtual existence to real existence, in which case it flies away, thereby robbing the black hole of energy. So how does that work? Well, mass is the source of the tidal force. So if the tidal force is doing work to make the particle a real particle, it has to pay for it by losing some of its mass. So the particle energy that goes away is paid for by having the mass of the black hole get smaller. When all is said and done, this process takes a long time, but what will happen, a solar mass black hole will last for about 65 cosmological decades. And the time scale goes like a cube of the mass. So that lets us understand the black hole era. Each galaxy has a big black hole and millions of small ones. The small ones have about 10 solar masses, over 20, so they will live for 68, 69, 70 cosmological decades. And then the big black hole in the middle will have 1 million to 1 billion solar masses, and it will live for 83 to 93 or so cosmological decades. But as you see, even the largest black holes will go away. If you had a black hole with the mass of the whole galaxy, it would evaporate in 98 cosmological decades. And just to show you that black holes are not forever, suppose you took every particle, and there's about 10 to 78 of them, if you take every particle in the observable universe today, and you were to ball them up into a black hole, that black hole would evaporate in only 131 cosmological decades. And there's no way to get material communicating with itself across the whole universe today. So there's no way we will make a black hole that massive. And what this means is that no matter, even though we don't know exactly what the largest black hole is, after about 100 cosmological decades, they will all come. So the black hole era will end if Hawking radiation happens, and we enter into the final era. So the dark era happens when there's no stellar bodies of any kind. There's only the particles left over from all of the processes that we talked about. as my colleague Greg Coughlin said on CNN, in the dark era, it will be very, very dark. However, you should never say never. Remember that the universe is now accelerating, and the cause of this acceleration might be some kind of vacuum energy. And if you have vacuum energy, you're saying that empty space actually has an energy level associated with it. Well, if you're going to buy that bridge from me, why not give me a second energy level? So you can say that empty space has an energy level, but there's a lower energy level accessible to it. If that's the case, then the universe can make a phase transition from a high energy state to a low energy state, giving you a new vacuum state. So the cosmos, at any time actually, could experience such a phase transition. And what happens is that little bubbles of the new phase nucleate in the old phase, like little tiny ice crystals nucleating in super cool water. And then under the right conditions, the bubbles can grow, percolate, and the phase transition can complete. So if you let me invoke the third if, remember we have the if there's more than one energy state, and if you can have a transition. Give me one more thing. Let me say that the field distributed the transition actually couples to something that affects the laws of physics, either the masses of the particles or the strengths of the forces. If all three of those things are true, then after the phase transition, you get a new version of the laws of physics. So depending on what those new laws of physics are, you can imagine the universe doing new things. Since we don't know what they are, I'm not going to calculate it for you. But it is possible in this way for the universe to get a new start. Now, you might think that at this point in the story we'd be starting to get a little bit speculative. So this is actually a good place to not quite end, but we will now wrap up. So, a couple points I want to make to end the story. We're now at Cosmological Decade 100 or so. I can calculate for you physical processes that will happen on 500 cosmological decades, 10 to the 500 cosmological decades, much longer than the timescales that we're talking about today. We've chosen to cut off this projection at this scale because we're starting to lose experimental contact. But some people will think that we've been very wimpy, I guess, and that we could go much further into the future. In fact, Freeman Dyson, in the 79 article that Joel mentioned, talked about the fact that since iron is the most stable nucleus, if you just have a rock with no proton decay, if you have a rock, everything will end up being iron. But that takes 10 to the 1500 years to happen. So that's 1500 cosmological decades, much, much longer than what I talked about here. The next thing I want to point out is that the fate of the universe is a little unsatisfying to some people. We started with a Big Bang moment, or whatever you would like to call it, but we started out with an expanding universe. And it went through this life of making structure and then killing its structure. So we have this trajectory of growth and death. And it's just a one-shot thing. It's like firing a rocket up once. There is no cycle here. Now, many people like the closed universe idea where you grow and then you recollapse and you grow and you recollapse. So you have a cyclic universe. And there's much literature on that. The honest truth is that there actually was never any data in favor of that. Ever. It's only that the error bars were large enough that you could get away with saying it. All of the data have always pointed to either a flat or open universe. And now that we know the universe is accelerating, again, never say never. One of these phase transitions could change the whole story in the future. But the data that we actually have in hand suggests we get this one-shot universe. So instead of relying on cycles to give you more universes, the story has changed so that instead of cycles, you get multiple universes, you get many shots. Our universe is one trajectory, one expansion event and eventual Musai decay. But this effect can happen in other parts of space-time. And that gives us the multiverse that you guys talked about a little bit this week, right? So, to summarize, with what we understand about both physics and astrophysics, we can construct a pretty good working paradigm for how the future of our universe, our own patch of space-time, will play out. And second, as I've emphasized, and we'll talk a little bit more on Monday, doing this lets us gain some understanding about our universe today. But there's two caveats that I want you to really understand. And one is that as I go from today's universe further and further into the future, quite frankly, we know less and less about what we're talking about. In other words, more and more uncertainty accumulates the further into the future you go. Now, to be honest, as Anthony was emphasizing earlier, the same thing happens as we go back in time. As we go further back in time towards inflation, towards whatever you want to call what happened before inflation, we have less and less experimental contact, and there's more and more uncertainty in our projections. So one of the things that I think philosophers might want to talk about is at what point do you stop doing science? In other words, how far into the future do you have to go before it's not science anymore? Clearly, when I calculate, or at least I think when I calculate the next 100 billion years, and I calculate what will happen to the structure of a halo, and I use that to define the mass of the galaxy, I would argue I'm still doing science at that point. But how far can I take that before you say, no, no more, you've left the reservation, right? That's an interesting question. And I think the same thing happens as I go further back in time, too. How many universes that I don't see can I invent before I'm no longer doing science? I just invented a whole bunch of them. And the other thing that you should keep in mind is that everything I've talked about makes an implicit assumption that we actually know what the laws of physics are. And we know a lot about the laws of physics, so it's a reasonable thing to take them and calculate them. But there could be surprises. One of the obvious surprises is that it's possible for the laws of physics to change over time. For example, the strength of gravity could change. Gravity could be stronger or weaker in the future. Now we have measurements. We know that the time scale on which gravity is changing is longer than about thousands of times the current age of the universe. So I'm probably good up to Cosmological Decade 14 or so. But after that, it's possible for gravity to have a time variation. It's possible for the electromagnetic force to be time variable. We don't have experimental data that forbid that. So that's another caveat. There could be changes both large and small in this projection in the future, depending on what the laws of physics really are. Even though, as Joel pointed out, a lot of physics was understood between 1979, when Freeman Dyson wrote his first projection, in 1997 and 99, when Laughlin and I did the next projection. In the intervening 10 years, we learned more about the accelerated universe, and some of the stuff that I told you about today is also newer than that, because we continue to understand more. It's not so much that the future projections are no longer right, it's more the case that we can build a much richer projection with what we now know. So I think I'm about out of time, so I think this is a good place to end, but we can have a few moments for discussion and pick it up this afternoon as well.
So, just a very general question about the strategy here. Suppose somebody described to me, say, the state of the Earth 100,000 years ago, and asked me to make a prediction about what the surface of an island at the bottom of the Hudson River was going to look like 100,000 years in the future. I might say, okay, I have basic laws of physics, I have laws of geology, plate tectonics, so on and so forth. I have laws of the ecology of the biosphere. I apply those, and I make a projection about what the surface of Manhattan is going to look like 100,000 years in the future. This projection will be really bad, okay? It'll be really inaccurate, okay? And the reason is I've used the wrong sciences, or at least there are other sciences I should have brought in. What I really should have been paying attention to are sciences like the economics and politics and cultural evolution of human societies and so on and so forth, because the surface of Manhattan has been profoundly affected by those, okay? And the projections I would have gotten if I applied geology and the ecology of the biosphere and so on and so forth to making projections about how Manhattan was going to look in 100,000 years, would have been way the hell wrong, okay? The question is there a reason to believe that this kind of worry isn't going to scale up, okay, over billions of years into the future? That is, there are all sorts of critiques all over the place of what you were calling the Copernican principle. Most of those, I guess, are theological critiques. They're not very interesting, okay? But there's another kind of critique that says, look, the evidence we have so far, that is the evidence, say, about the structure of the surface of Manhattan over the past 100 years, indicates, says, gee, maybe you ought to be careful about things like the Copernican principle. It turns out that the existence of human beings, as opposed to other animals, turned out to be an extremely important factor in determining the structure of the surface of the island of Manhattan over the past 100 years, okay? And technology is quite young. It's only a couple of thousand years old, so on and so forth. Isn't there a worry that over billions of years this could scale up? And just as it turned out to be the case that, say, geology and plate tectonics and the ecology of the biosphere turned out to be largely irrelevant to the future shape of the surface of Manhattan, okay? Maybe there could be all kinds of senses in which standard astrophysical considerations turn out to be largely irrelevant to the future structure of, say, the solar system or the galaxy or something like that.
Well, you've asked a number of questions there. So let's back up to your first one. You said, what is my strategy? So I think it's important that to outline the basic strategy is that I play the role of a physicist, right? I'm not a futurist. I don't know about economics. I don't know about biology. I don't know about future civilizations. I would also argue that nobody does, but I certainly don't. So the strategy is to see what physical processes will play out over the next 10 to 100 years, and astrophysical processes, and we as physicists have equations that can calculate them.
Right.
There are no equations that I know of or that I would trust that will tell me how people in the future will build, extensions to the land of Manhattan. Nor do I actually care. It's not a physics problem. It's not.
Wait, that I don't get. Suppose the question is to predict what's going to happen to Manhattan. That's the problem.
But
Then the question is whether geology is the relevant science or economics is the relevant science.
Right, but see, I'm a physicist and I want to know what happens to the physical universe due to physical law. That's the problem I'm seeking to solve. If you're interested in a different question, you go calculate it. That's cool. But you can't put your problem onto me.
So the question isn't to try to figure out what the universe is going to look like?
Well, I'm trying to do that within the physical world. If you're going to say that civilizations will sculpt the galaxy,
isn't that a physical effect?
Well, I think it's a physical effect, but there's absolutely nothing I can do about that problem.
Good. So maybe the thing to say.
So I think the first
we
step.
don't have good methods of projection.
Right. See, in physics, we always do the spherical problem first, right? So I would say, and the strategy that I adopt with my colleagues is to say, well, first step is to see what laws of physics do to the physical universe. That's the first step. Then you can start worrying about civilization and so on. But the first step is to understand how a star is going to evolve. Then you can worry about how some future civilization may not affect the evolution of that star. But the first step is to understand the star. And that's as far as I've gotten. And I'm not claiming, keep in mind all of you, I am not claiming to have gone any further than that. In fact, I'm not even claiming to be done with that.
Right.
There is much more we can do. But I think you do raise a very good point that civilization, people, external actors, I guess they're called, will in fact mess up these projections. But I have no equations to describe that.
Right, sure.
So I'm not sure what I can possibly do to answer
Right.
your question in terms of what's going to really happen to those actors.
Good, good.
And I would actually challenge you, I doubt you know as well.
But, no. Yeah. No, all I know is that I can see examples where the sciences that you might think would be relevant, say in this case, geology, ecology of the biosphere, those turn out not to be the relevant considerations.
Okay, let's have a quick question from Joel, then I'll get to you guys.
Well, it's really more of a remark. So, Fred did, working with his colleagues at Santa Cruz, calculate the story of how Earth could be moved steadily further from the sun. And that's a small example
Right.
of sort of solar system engineering.
Yeah.
And one
Right.
can imagine, and Freeman Dyson in fact has imagined, much more dramatic examples of
Like Dyson's spheres.
right,
Yeah,
like
I was
Dyson's
thinking
sphere.
of Dyson.
Right.
Right.
So one can certainly imagine that there could be, at least on scales of solar systems, some fairly significant
Oh, yeah.
engineering. And it's also certainly possible on timescales of a few millions of years for human-based either life or robots or something to explore and ultimately populate an entire galaxy. As far as we know, we're the first intelligent creatures that have embarked on what Deutsch calls the beginning of infinity. And there's really no easy, unless we destroy ourselves, it could certainly expand tremendously. And we humans could be the beginning of that. So it's also true, if the cosmological constant is the dark energy, that we're surrounded by an event horizon which ultimately is going to be empty. Our local group, Milkometa or whatever you want to call it, is going to be all it is, at least as far as we know. So the entire future of the visible universe can depend on what we do. Just wanted to leave you with that thought.
Yeah, so Anthony, you could mention.
Yeah, I wanted to follow up on that one because it's a fun one. We've got along Joel's line of thinking, we've got a limited time to save humanity, that humanity could last really to these really huge time scales. Because if we don't if we were to populate more or less our own horizon volume, then that will kind of split into multiple horizon volumes, and each one of those can keep populating and keep going. But if we get kind of stuck within this one, then I think we're more or less stuck. We're not going to make it to another horizon volume, and we're stuck within this one. And one place where that could get important, if you really care about the very long-term future of humanity, is with vacuum decays. Matt told us, and I didn't realize this, but I looked it up, and I think it's true. Of course, I believe him when he said it. That the standard model is actually unstable to vacuum decay, and the current mass of the Higgs, where it's constrained, leads to an instability that could be, significantly shorter than some of the timescales that we're talking about. So we're doomed even from the standard model if there isn't other physics to fix it. Now, if there are vacuum decays, one thing that you said, which I would say is just technically not quite right, is that if we have vacuum decays, they won't percolate. Because we have a vacuum energy, you'll basically have the picture of eternal inflation with bubbles forming. The bubbles will not have a chance to percolate.
Yeah, no, to be careful, I was actually careful to say, under the right circumstances, if they percolate. Because I do know.
Well, they would never percolate because the time scale for decay is longer than the Hubble time.
Well, that's if you have a constant cosmological constant. Right? You can have time varying cosmological constants. That for the future, we have no idea.
Yeah. Okay.
Yeah. So anyway,
but if we manage to spread out to other Hubble volumes, we can win because even though the vacuum is decaying and will eat up most of the universe, if we manage to keep spreading out, we basically will be eternally inflating, and the vacuum decay will never be able to kill us off.
So, back to your conviction, I can go to him first since you have any questions.
Yeah, I would just like to follow up on what David was saying, and I would argue that even if you just take the physicist's perspective, you always have some fundamentally incomplete knowledge of physics and also of observations that will spoil your ability to make predictions. So, for example,
Well, I think this point here.
yeah. No, but suppose you were an observer during radiation domination, okay, in the universe, say before recombination, for example. I would argue that no observation that you possibly performed would have told you that there was a cosmological constant. So if someone asked what was the expansion rate 13 billion years in the future, you wouldn't have any possibility of predicting what we are observing right now. And at the same time, now we don't know what dark energy is. So you only have a measurement of the density, the energy density, and the equation of state, but you don't know what dark energy is. And there is this paper by Cruz and Copernican that says that no observation you can conceivably mean on dark energy, unless you know what it is, will tell you what the future destiny of the universe is, right? Because even if you have something which is compatible with W equal -1 and the present day vacuum energy, you cannot extrapolate that arbitrarily in the future. So I know that you're saying that, but I just comment on this.
No, I think I agree with absolutely everything you said. And, many of those thoughts were in my mind when I wrote that sentence. We do have to be careful. But given that we only have the data we have, the exercise, the program, is to take what we have and project it and see what kind of sense it makes. But one should never take, any calculation more seriously than it deserves to be taken on. So, and that certainly applies here. Okay.
Yeah, following up on David's question, on a recent question, it seems to me that your program is basically saying, given the laws of physics as we know it, let's calculate what would happen to the far future as far as we can see.
Of the physical universe.
Of the physical
Not
universe.
the biological universe.
Sure. Yeah.
Because another thing that one could do, and that Freeman Dyson is braver than me, he's probably smarter than me too. He wrote down a scaling hypothesis that tells you how life will evolve in the future, or how many ticks of consciousness you can have, and sort of biological things. And I have steered clear of those as well.
Sure.
You don't need to, but I have not presented those to you.
Fair enough. But it seems what you've done is you've done everything explicitly saying, if you ignore any of those speculative things about biological processes in the future of life. And first of all, it's interesting because it's fun. And second of all, it's interesting because this gives future life the information they would need to say, how do I make changes to my environment, to the galaxy, to the Hubble volume, in order to let life survive into the infinite far future, or at least as far as possible. So that's
right. As I was telling you, this is just half of the first step, right?
mm-hmm.
We'll get to the rest. Well, we'll never get to the rest, but we could get to the rest.
But yeah, it's absolutely true that the speculation about the future of civilizations is all science fiction at this stage. But it's still this is still a great first step.
Well, I don't in any way mean to criticize those who want to project civilizations and such in the future. I'm only making it clear that I don't know about it myself. I applaud anyone who can make progress in that.
Here's, just to put it a little differently, here's what the argument would be if one wanted to put it in its strongest form.
Okay.
The existence of things like, physical systems that do science and technology, okay, represents, or one might want to argue that it represents a radical instability, okay, a radical form of extreme sensitivity to initial conditions in the future physical evolution of the universe. Maybe that's true or maybe it's not. okay? The kind of strategy that's being pursued here, I take it, is implicitly assuming that it's not, okay? But somebody could say, given, say, our past experience of the evolution of the surface of the island of Manhattan, or something like that, it looks like circumstances in which there are these kinds of information gathering and processing physical systems in the world, okay, especially over long periods, introduces a fantastic sensitivity, a chaotic kind of sensitivity to small distinctions in initial conditions that, like chaotic situations do, tend to ruin predictions like this. That's the worry.
Yeah, no, I was perhaps a little bit overly negative in my first response, because I mean, I agree with that.
Right.
I would correct or amend what you said there at the end a little bit. If you have a chaotic system for any reason, whether it's because of people or
Right.
other reasons, it does ruin a particular class of predictions. But what it really does, if you think about it, is it changes the questions and the answers you get, right? Just like when we went from a particle description to real quantum mechanics, we no longer ask, well, where's the electron around the atom? We say, what's the wave function? Very different question. The first question doesn't actually have a sensible answer. The what's the wave function question does have a sensible
Right.
answer. If you have a chaotic system, then, like solar system is chaotic, right? So you cannot ask, turns out you cannot ask where Jupiter will be in its orbit 7 billion years from now. It's a nonsensical question, just like quantum mechanical electron positioning.
Right.
But what you can, just like for the electron, you can say, well, what's the wave function? The right question there is, what is the probability distribution for the locations of Jupiter 7 billion years from now?
Right.
That's a completely well-defined question.
Right.
It costs an enormous amount of computing to answer them, more than you think. So we don't actually have enough computing done in the whole world to answer that question.
Right.
But in principle, we could if we worked hard enough at it. So chaos changes the questions you ask and the answers that you would produce to answer.
Right. Right. And it typically, like you said, spreads the probability distributions
Right.
out. So fine.
But again, I will come back to what I said earlier, is that point well taken. It will happen. Civilizations can change the physical universe. We've seen it happen in Manhattan. But I still argue the first step is to understand what physics does to physical objects. And until I understand that fully, I'm going to put off the rest of your program until I finish the first of mine.
Sounds reasonable.
So I think that's a good way. You have a question?
Yeah, it's just kind of a follow-up sort of on this point. So this kind of problem might be new to physics, but it's something that's been around in other sciences for a while. So you can think about economics, right? So say you're a really good economist and you predict the recession really well. It seems like but it seems like the better you get at predicting recessions, the more likely it's going to be that governments are going to start looking at your predictions and then trying to undermine them, right? So it looks like the science is somehow self-undermining. Now imagine you as a philosopher of science go up to the scientists and are like, hey, you're really screwing up, aren't you? Like the more predictions you make, the more they get undermined. It seems like this is a problem for you, this is a problem for your science. It's just going to be bad at prediction. The right response for the economist is not, I think, to say, you're right, this is a problem for me. The right response is to say, oh, you're just confused about what I'm doing. I'm not trying to make predictions in the sense of telling you exactly what's going to happen. What I'm trying to do is give you tools for manipulating possible future situations. So what I'm doing is like telling you sort of certain sorts of conditionals that are going to allow you as the decision maker to act properly about the future. So similarly here, we might think what we're doing right now is saying, here's what will happen if no one does anything, right? And that's a really important thing. You might want to call that a prediction. It could be that, you know, the better of a prediction it is, the less likely it is to happen, because if you think that's not good, we're going to act. This is a problem. This is actually a
that sounds like the right way to think about it.
That is a good way to think about it. In fact, I was very careful most of the time to use the word projection instead of prediction because of all of these caveats that we've been talking about for the last 20 minutes. this one as well as the fact that laws of physics can change and so on. So this is a projection based on very specific things. Laws of physics, initial conditions we have today. Maybe we're not measuring our initial conditions today as well as we think we are. Astronomers are not infallible as good as they are, right? So there's lots of other caveats as well. So this is a projection, not a prediction. And I agree with you.
And it's like saying, you know, this is what would happen if life plays no major role in future history.
Right.
And that's not to say that civilizations can't play one.
Right.
It's only to say I don't want to calculate them.